Multiple inheritance allows a single class to inherit features from more than one parent class simultaneously. While this is a powerful tool for code reuse, it introduces a specific challenge. If two parent classes provide a method with the exact same name, Python needs a clear rule to decide which one to execute. This rule is known as Method Resolution Order or MRO. To understand why MRO is necessary, let's consider the analogy of a person named Arjun, here on the left. Arjun has two roles, or parents. He is a doctor and a martial artist. From his doctor role, he learns to heal, diagnose, and undergo clinical training. From his martial artist role, he learns to fight, meditate, and undergo combat training. Notice that both roles provide a method related to training. If Arjun says he is going to execute his train method, we need a system to decide if he means the clinical training or the combat training. This is where MRO provides the precise, predictable rule book that Python follows to make that decision every single time, ensuring there is no guesswork involved. The fundamental logic of MRO follows a specific path. Python reads your class definition from left to right and then moves upwards through the inheritance hierarchy. Looking at figure 1.1, we see a code example. A child class that inherits from parent A and parent B. This visual shows the search path Python takes. First, it looks for a method in the child class itself. If it doesn't find it there, it moves to the first parent listed in the parenthesis, which is parent A. If it's still not found, it moves to the next parent listed, which is parent B. Finally, it moves up to the universal base class object. Down here, there are three key points to remember regarding this process. First, you can always inspect the exact lookup order of any class by using the built-in MRO attribute. Second, Python manages this using the C3 linearization algorithm. While the name sounds highly technical, it simply ensures the search order is consistent and never enters an infinite loop. Third, the industry standard way to use multiple inheritance is through Mixins. Mixins are small, focused classes designed to add one specific capability rather than defining a whole new type of object. One of the most famous challenges in multiple inheritance is the diamond problem. This happens when two classes inherit from the same base class and then a fourth class inherits from both of those middle classes, creating a literal diamond shape in the hierarchy. Let's look at figure 1.2, which illustrates this using a biological example. At the top, we have living being. Below that, we have two classes, flying creature and swimming creature, both of which inherit from living being. Finally, at the bottom, we have duck, which inherits from both flying creature and swimming creature. Without a clear MRO, if living being had a method that was overridden by both the middle classes, the duck class wouldn't know which version to use. However, Python's MRO for duck follows a specific predictable chain shown here on the right. First, it checks duck, then flying creature, then swimming creature, then it moves up to living being, and finally object. By visiting every class exactly once and following that left to right then up approach, Python completely eliminates confusion and prevents the logic from looping infinitely. This clear resolution path is exactly why we can safely build complex behaviors by combining smaller specialized Mixin components. In professional software development, particularly when building microservices, we leverage this predictability to construct powerful systems out of simple reusable Mixin components.
In professional software development, particularly when building microservices, we use multiple inheritance to construct complex systems out of small, reusable paths. Instead of building one giant parent class that tries to contain every possible feature, which quickly becomes tangled and hard to maintain, we rely on what is known as the mix-in pattern. Notice how we can break functionality down into small, highly focused mix-in classes. In this top example, engineers have created a logging mixin just for recording activity, a caching mixin for remembering data, and an auth mixin for verifying permissions. When we need to build a new service like this user service class in Python, we simply combine these mixins along with a base service. This approach makes our code remarkably clean and modular, allowing us to snap features together just like puzzle pieces. Let us look at a real-world example of this design in Django, the framework behind massive platforms like Instagram. Imagine we are building an admin dashboard web page. The specific view has three distinct requirements. The user must be securely logged in, they must possess admin permissions, and the system still needs to handle standard HTTP logic. Instead of writing a complex web of if-else statements, the developer handles this elegantly by combining mixins. If you look at the admin dashboard view code, it simply inherits from three targeted classes. Because of this structure, the login required mixin takes full responsibility for redirecting unauthenticated users. The permission required mixin steps in to block anyone without adequate admin rights. Finally, the standard view class takes care of the actual web communication. The core takeaway is that the Mixin pattern uses multiple inheritance to let each class handle exactly one concern, eliminating code duplication and making your architecture incredibly flexible. To see this in action, we are now going to write our own IoT sensor management system from scratch.
Let's look at how we can apply these mixins to an IoT sensor management system for a factory. We start by defining three separate mixin classes, each with a single clear responsibility. First, we have the logging mixin. Its entire job is to handle recording activity. It grabs the current date time and uses self.class.name to dynamically identify which specific sensor is reporting. This ensures we get a nicely formatted, consistent log line every time. Next is the alert mixin, which adds the ability to send notifications. It uses a dictionary to map severity levels like info, warning, or critical to specific icons. This visual cue helps operators quickly identify the urgency of any message at a glance. Then we have the data storage mixin to manage the sensor's historical data. It maintains a private readings list. It provides straightforward methods to store a new reading securely, retrieve a copy of the readings without exposing the original list, and calculate the average of all recorded values. Now, apart from these helpful mixins, we define our core sensor base class. This holds the essential identity of any sensor in the system, storing basic properties like its ID, location, and the unit it measures. Here is where the magic of composition happens. We combine all of these independent pieces using multiple inheritance to build a complete temperature sensor. Notice how it inherits from the logging mixin, the alert mixin, the data storage mixin, and finally the base sensor class. When the read temperature method is called, it seamlessly uses all those inherited abilities. It stores the reading using the data mixin, logs the message using the logging mixin, and sends an alert using the alert mixin. Specifically, if the temperature reaches 85% of the safe limit, it issues a warning. But when it exceeds the maximum safe limit, it triggers a critical alert. All of this works reliably because of Python's method resolution order. If we look at the MRO for the temperature sensor, we see exactly how Python searches for methods, starting at the temperature sensor itself, then checking logging, alert, data storage, and finally the base sensor class. Let's move on to discuss how these principles apply to a broader system architecture.
Let's bring all these concepts together to solidify your understanding. Think back to the classic diamond problem we might see in a banking system. If a premium account inherits from both a savings and a loan account, we face ambiguity over which balance method gets called. This complexity is exactly why we use mixin principles. Instead of deep tangled inheritance trees, we want our classes to be small and focused. They should provide just one specific capability, like logging or caching, acting like modular puzzle pieces. Let's apply this practically by designing a smart home system. Looking at the requirements here, we define specific mixins for network connectivity, scheduling features, and energy tracking. Over in the architecture diagram, notice how these independent mixins can be seamlessly attached to our base smart device class. When we write the actual implementations, we simply combine them to create distinct products like a smart light or a smart AC. Each final device inherits its core identity from the base class and dynamically pulls in exactly the capabilities it needs from the mixins while adding unique methods like setting the temperature. To wrap everything up, let's look at the quick recap. We know that multiple inheritance gives a child all the methods from its parents. When conflicts inevitably happen, Python safely resolves them using the method resolution order, checking left to right, then up the tree. But to avoid confusion entirely, the professional best practice is to rely on small, focused mixins that are never used on their own. The golden rule for your software architecture is this. Use regular inheritance when your object fundamentally is a specific type, like a sensor, but use mixins when your object simply has a certain capability, like logging. You are now equipped to build complex, modular, and maintainable systems using Python's inheritance rules.